Now in this recording I will show how to find the solution to a set of two simultaneous differential equations. So in this case we've got dx dt, which is 6x of t minus 3y of t, and dy dt is 2x of t plus y of t. So that means we've got the first differential equation containing x and y on the right hand side, and the second as well. Now our initial conditions are that x of 0 is 3 and y of 0 is 5. So of course the solution we're after is a function x in t and a function y in t. And these two functions have to fulfill both differential equations. So what do? First of all, we're going to find the Laplace transforms of the two equations. So I've got Laplace transform of dx dt, which is 6 times the Laplace transform of x of t minus 3 times Laplace transform of y of t. And the second equation becomes Laplace transform of dy dt is equal to 2 times Laplace transform of x of t plus the Laplace transform of y of t. Now these two equations I will always have to keep together now because they both have to be fulfilled. So on the next step, the Laplace transform of dx dt, look this up on the table, that is s times Laplace transform of x minus the function little x at 0. And on the right hand side I've got 6 times capital X, Laplace transform of little x, minus 3 times capital Y, Laplace transform of little y. And for the second equation I've got something similar, only that we now are dealing with y. So I've got s capital Y minus little y of 0. And that is 2 times capital X plus capital Y. Now I have transformed the original differential equation in the time domain into two much simpler simultaneous equations in the frequency domain. And we're now going to solve these two equations for capital X and for capital Y. But before we do anything else, let's just substitute in the initial values. So x of 0 is 3, so I get minus 3 here, and the right hand side stays the way it is. And for the second equation, a similar thing, y of 0 is 5, so I get minus 5 here, and that's equal to 2 capital X plus y. So one more step. I'm going to rearrange this so everything with capital X and capital Y is on the left hand side and all the constants are on the right hand side, which is then the typical setup for a set of linear equations when we start solving them. So I'm going to move the 6x to the left hand side, the negative 3y goes to the left, and the negative 3 goes to the right, and I'm doing a similar thing for the second equation. I will also factorize straight away, and I will get s minus 6 times capital X plus 3 capital Y is equal to 3 for the first equation. For the second equation, make sure that you've got x first and then y. So this becomes a minus 2x and plus s minus 1 y is equal to 5. So these are my two equations. So I'm just going to tidy up a bit here. So these are my two equations now. I'm going to solve these using Cramer's rule. That means that capital X is going to be delta 1 divided by delta. Now delta is the determinant I get by using the coefficients in front of the x and the y, just the way they're listed here. So I get s minus 6, 3, minus 2, and s minus 1. And delta 1 is the determinant where the right-hand side coefficients are replacing those for the first column. So I get a 3 and a 5 here. And the coefficients for y stay the same. So this is going to be in the numerator I get 3 times s minus 1 minus 15, and in the denominator I get s minus 6 times s minus 1 plus 6. So if I simplify this further, I get 3s minus 18 in the numerator, and in the denominator I will get s squared minus 7s plus 12. So this is my capital X, which is the solution in the frequency space for X. Now I'm going to do the same thing for Y. I might just write it down here. So that's delta 2 over delta. So delta 2 is the determinant of, well, we would keep the coefficients for X, s minus 6 and negative 2, and we place the right-hand side coefficients in there instead of the Y coefficients, and divide this by the same matrix, same determinant as we had before for X. So what we get, of course, is the same down here because we haven't changed anything there. And in the numerator we've got s minus 6 times 5 plus 6. So that comes to 5s minus 24, and the denominator is still s squared minus 7s plus 12. So let me tidy this up again. In order to transform capital X and capital Y back into the time domain with little x and little y, we need to do something about these expressions, because we can't just read off the table how these should be transformed back. So first of all, I'm going to factorize the denominator. It can be written as s minus 3 times s minus 4. And the top I'm going to leave for the moment, 3s minus 18. So in the next step, I'm going to use partial fractions, which means I'm going to rewrite this as a over s minus 3 plus b over s minus 4. And so the task now is to find a and b, because once we've got these two, we can easily find the inverse of this Laplace transform. So how do we do this? Now in this equation here, I'm going to multiply both sides by s minus 3 times s minus 4. And what I get then is on the left-hand side just 3s minus 18. And on the right-hand side I get a times s minus 4 plus b times s minus 3. Now if this is meant to be true for all s, that means I can choose any s. And I'm going to choose those s that make one of those variables disappear, a or b. In this case, let's start with s equal to 4. If s is 4, I have 12 minus 18 on the left-hand side, so that comes to negative 6. And on the right-hand side, this bit disappears, and what's left is b times 1, so that's b. So there already is my b equal to negative 6. I'll do the same thing with s equal to 3. And we'll get 9 minus 18, so of course that's negative 9, is equal to a times negative 1, so that's negative a. And that means that a is equal to 9. I've got the second value here. So that means that I can rewrite this as 9 over s minus 3 minus 6 over s minus 4. Let me tidy up again. So now it is going to be really simple to find the inverse Laplace transform. So this inverse Laplace transform is at the same time little x of t. And, well, that is going to be 9e to the 3t minus 6e to the 4t. So that's the first part of the solution. That's little x of t. Now I'm going to do the same thing that I've just done for capital X to capital Y. So I'm going to write this as 5s minus 24 divided by s minus 3 times s minus 4. And I'm going to find an a and a b that fulfill this equation. So this means that 5s minus 24 is equal to a times s minus 4 plus b times s minus 3. And that means I might just tidy up a little bit. If I sub in s equal to 3, I get 15 minus 24 is equal to minus a. So that means 15 minus 24 is of course negative 9. That means a is equal to 9. And I do a similar thing for s equal to 4. So I have 20 minus 24, of course that's negative 4, is equal to b. So b is negative 4. So these are my two solutions here. So that means I can write this as 9 over s minus 3 minus 4 over s minus 4. So if we now find the inverse Laplace transform of y, which is of course little y of t, that is simply going to be 9e to the 3t minus 4e to the 4t. So now we've got our solution. Let me just tidy up once again. So there it is. Now let's do a very quick check to see if this is really the correct solution. And for that we're going to put x and y into the equation up here. So first of all, let me calculate dx dt. That is going to be just the derivative of this here. 27e to the 3t minus 24e to the 4t. And I also calculate dy dt. That is 27e to the 3t. That's the derivative of this here. Minus 16e to the 4t. So that's the left-hand side of each of the equations up there. Now the right-hand side, let's put that together. What is 6x of t minus 3y of t? That is going to be 6 times this up here. So 6 times 9 is 54 e to the 3t. Minus 6 times 6 is 36 e to the 4t. That's the first part here. And then I've got minus 3y of t. So that means minus 3 times this here. I might actually multiply this out while I'm going rather than write down everything step by step. So I have minus 3 times 9 is minus 27 e to the 3t. There's a minus and a minus, so this becomes a plus. 3 times 4 is 12 e to the 4t. So this now simplifies to 54 e to the 3t minus 27 e to the 3t, so that's 27 e to the 3t. And minus 36 plus 12 e to the 4t is minus 24 e to the 4t. Now let's check. This is the right-hand side of our equation up there. And the left-hand side was here. So this is indeed equal to that. Perfect. Let's check the other equation as well. It is unlikely that this has gone wrong, but let's check it in any case. So what I need is 2x of t plus y of t, the right-hand side of the second equation, and that needs to be the same as the dy dt we've calculated here. So 2 times x of t was this here, is 18 e to the 3t minus 12 e to the 4t. And then plus y of t, so that's plus 9 e to the 3t minus 4 e to the 4t. That simplifies to 18 e to the 3t plus 9 e to the 3t is 27 e to the 3t. And minus 12 minus 4 is minus 16 e to the 4t. Let's have a quick look. This is indeed the same as that. This is the same as that. So that's correct as well. So we've also shown that this is indeed the solution. This is the solution to the system of differential equations.